Based on this, we give the first, or you can say a primary definition of probability. It is called classical or mathematical definition of probability. This definition is due to Laplace, which was available in his treatise on probability in 1812. Now, this is based on certain conditions. I have already introduced the concept of several events. So, these are all subsets of the sample space. We may call events say A1, A2, AN to be equally likely. Now, this is some terminology which is like circular in nature. Let me again explain. So, I will say events A and B are equally likely if A and B have the same chances of appearing. Now, till now we have not defined what is the chance. So, this definition itself looks circular, but anyway, this is what has been used in the classical definition of probability. Suppose a random experiment has n possible outcomes which are mutually exclusive, exhaustive, and equally likely. So, that means we are looking at the elementary outcomes of the random experiment which are collected in the sample space. That means the sample space has a total of n points, which is a finite number, and naturally then when we are describing all of them, they are supposed to be mutually exclusive, and we have exhausted all the possibilities. So, I am making an assumption that they are equally likely. Let m of these outcomes be favorable to the happening of event A, then the probability of A is defined by probability of A is equal to m by. So, this definition was given by Laplace because of the earlier statements which I gave, that the probability theory has origin in the games of chance, such as tossing of a coin, throwing of a die, the numbers coming on a roulette wheel, etc. So, all of are drawing of a card in a pack of cards. So, all of those experiments had a peculiar thing, that they had a finite number of outcomes, and assuming that the game is fair. For example, if you toss a coin, so you assume that it is a fair coin. If a die is thrown, then you consider that it is a fair die, etc. If it is a pack of cards, then you assume that it is a pack of well shuffled cards, 52 cards. So, these assumptions seem to be valid there, that is exhaustive, mutually exclusive, and equally likely, and therefore, this definition was given, and this is the one which is used in the calculation of the probabilities in the classical examples. So, main disadvantages, or you can say drawbacks of this definition are that n need not be finite. For example, if we are considering the number of trials needed for the first success, then we do not know when we will stop. Suppose we are considering life of a bulb, suppose we are considering weight at birth of a child, then all of these outcomes, the collection of outcomes is an either countably infinite or uncountably infinite set. Then second is the more crucial thing, that we are saying that the outcomes are equally likely. Now, equally likely thing means that we are knowing that the coin is fair or the die is fair or the pack is well shuffled, etc. But that is bringing in an inherent understanding of the definition of probability, whereas we are actually defining probability now. So, it is a circular definition. The definition is circular in nature, as it uses the term equally likely, which means outcomes with equal probability. Similarly, in a given experiment, we may not be able to express the outcomes as mutually exclusive outcomes. We may not be able to exhaust all the possibilities of the outcomes, because the total number of possibilities may be really large to describe. So, this definition, though quite useful in the beginning of the development of the subject, has its limitations. Later on, a more important, or you can say a more practical or a more applicable definition was developed, which we call relative frequency definition of probability, which is based on actual conducting of the experiment. So, we can also call it empirical, because it is based on the actual observing of the outcomes, or a statistical definition of probability. The form of this definition is due to von Mises. Suppose a random experiment is conducted a large number of times independently under identical conditions. Let An denote the number of times the event A occurs in n trials of the experiment. Then we define the probability of the event A to be limit of An by n as n tends to infinity. Provided the limit exists. Let me give an example of the actual application of this definition. Let us consider, say, a trial of conducting tossing of a coin, and we want to find out the probability of head. So, this we are doing because we do not know whether the coin is fair or not. In the classical definition, we assume that the coin is fair, and then we try to find out probability of head or tail, etc. But suppose I do not know that a coin is fair, I actually want to find out the probability of head. Suppose an experiment of conducting of tossing of a coin results in 2 heads followed by a tail. Now, let us look at the sequence An by n here. So, the sequence An by n here, if you make it, in first trial you have a head and we are interested in the occurrence of head. So, an by n is 1 by 1. In the second trial again there is a head, and therefore the ratio an by n is 2 by 2. So we are looking at the event is occurrence of head. So if I look at the third trial, then in the third trial tail has occurred. So the occurrence of head is 2 and the total number of trials is 3. Now if we just continue in this direction, we can write the sequence an by n like 1 by 1, 2 by 2, 2 by 3, then it becomes 3 by 4, 4 by 5, 4 by 6, etc. And now in order to calculate the probability of head, we need the limit of this particular sequence. So in order to do that, let us write a proper mathematical expression for this. We can write it as, say, 2k minus 1 by 3k minus 2 for k equal to 1, 2, etc. We may write it as 2k by 3k minus 1 for k equal to 1, 2, etc. If the number of the trials is of the form 3k, then it is 2 by 3. by 3k for k is equal to 1, 2 and so on. So in each of the cases we are able to describe the ratio an by n, and it is very obvious now that if I take the limit of this as k tends to infinity, that is n tends to infinity, then the limit of this is 2 by 3, and therefore probability of occurrence of head is 2 by 3. That means it is a biased coin in favor of head. Now the relative frequency definition seems to be the one of the most reasonable definitions of probability, in the sense that it is based on the actual experience, and that is what the subject probability should be all about in terms of statistics. For example, if we are looking at the age at death of a person, then it should be based on the experiment, that is really how many people survive beyond the age 60, beyond the age 70. That means it should be based on the recorded age at death for the various persons. If we want to find out the sex ratio in a population, then we should look at how many children are born as male and female. So it should be based on the actual data. If we want to say something about the rainfall, then we should know in the past 10 years or in past 50 years what is the pattern of the rainfall during monsoon season. Therefore, this relative frequency definition seems to be the most useful definition for calculation of the probabilities. However, even this definition has certain drawbacks. For example, we are making an assumption that the experiment is observed, but there may be certain experiments where we may not be able to look at the observations. The observations may be less in number, or they may be too complex, too complicated, too costly. For example, if we are looking at the failure rate of launched satellites, then it is not an experiment which can be conducted every day. And if we are looking at from a country like India, then the overall launches of the satellite itself may be limited to a very small number, and therefore in order to find out the probability of a successful launch may be quite complicated. Although we are not saying that this type of calculation of probabilities is impossible, but it is difficult certainly if we want to look at the full experiment. However, the probability can be calculated using certain rules of probability by splitting the entire launch of satellite into various sections or various segments, and then we combine the probabilities of those various things. So the actual conduct of the experiment or actual observation of the experiment may not be possible sometimes. Also, there are certain experiments which are destructive in nature. For example, we want to look at how many of the matchsticks kept in a matchbox are useful. So conducting of an experiment means that we actually light a matchstick and observe whether it is giving good result. That means it burns, the full stick burns, etc. So this kind of experiment is destructive in nature because it will lead to the destruction of the material itself. And similarly, there are various experiments conducted to test the strength of the materials. Then it means that you apply a certain pressure on the material which is used for making of certain mechanical things, such as say a car or an engine or a train line. So the strength of the material is very important. However, the testing requires that you put some compressible force on that and observe it to break at a certain force, and then we estimate that how much actual force will be required. If the actual force which is going to be applied on that material is less than the breaking strength, then we say that the material is all right. So however, such experiments are also costly in nature, and sometimes it is skipped in order and it is replaced by certain other process to measure that strength. Sometimes this probability relative frequency definition may give a result which may not be very intuitive. For example, if I say the probability of an event is 0, then you must feel that the number of occurrences in experiment for that particular event must be 0. However, here since it is taken as a limit, so we may have say root n as the number of happenings in n trials, and if I consider the limit of this, then this is 0. So although the number of occurrences is not 0, but the probability of the event is 0. Similarly, we may have n minus root n by n, which will converge to 1. So every time the event does not occur. However, the probability is 1, which indicates that this is a sure event. However, we may treat it as in the sense that it means that the number of occurrences is negligible in comparison to the total number of trials. Again, this may lead to a little bit of confusion. For example, I may consider n to the power say 1 minus epsilon divided by n, where epsilon may be a very small positive number. Now here again this will go to 0. However, this will not be negligible number. So now it is negligible in the sense that if I look at the order, then in the terms of order, the order of n is more than the order of n to the power 1 minus epsilon. So this type of justification can be given for the relative frequency definition. Now we may now we consider a more rigorous definition of the probability. The first two definitions which I have given, they are based on the you can say they were based on the basic development of the subject of the probability itself. For example, the mathematical definition was developed as a consequence of the interest of some of the gambling houses to know probabilities of certain events, and they contacted the mathematicians of that time, and they looked at the entire thing as a finite set of outcomes which may be equally likely, and they gave the rules of the probability based on that. The relative frequency definition or the statistical definition is similarly based on the experience. So when people were really looking from the statistical point of view certain events, and they were not necessarily the events of the type where you have only head or tail or coin tossing, etc., then they looked at that how many times the actual event occurs during a certain number of trials. As we have seen that the definitions have drawbacks, and therefore they are not universally applicable. In order that a theory be consistent or universally applicable, we need certain axioms. So in 1933, the Russian mathematician Kolmogorov, he gave what is known as the axiomatic definition of probability, and this is based on the set theoretic development which we gave in the very beginning, that is on algebra of sets. So now we describe what is axiomatic definition of probability. What we have is that given a random experiment, we have a sample space, and now certain subsets of omega are the events which may be of interest to us. We may not be interested to consider all subsets of omega. So what we can consider is, we can consider a sigma field of subsets of omega. So, a sigma field of subsets of omega will consist of certain events, then their unions, their complementations, their intersections, their differences. In other words, if we are considering certain events, then all the manipulations of those events which are of interest to the experimenter will be included in the set V, and therefore, this definition of sigma field is useful in development of this definition, or you can say axiomatic definition. So, given a random experiment, we are considering a sample space and B a sigma field of subsets of omega. That means, in the terminology of probability theory, this is a set of events. So, omega B is called a measurable space. And now we are interested to define the probability. So, for every event which is included in B, we must be able to define the probability function. So, the axiomatic definition of probability, it is due to Calmo Guru. Let omega be a probability, be a measurable space. A set function P from B to R is a set of real numbers, is said to be a probability function if it satisfies the following three axioms. I will call them P1, that is, probability of A is greater than or equal to 0 for all A subset of B. The second axiom is that the probability of the sample space is equal to 1. The third axiom is that for any sequence of pairwise disjoint subsets EI belonging to B, probability of union EI is equal to sigma probability of EI I is equal to 1. This last axiom is known as the countable additivity axiom. The first axiom is known as non-negativity axiom, and the second axiom is known as the axiom of completeness. So, we will continue from here. We will look at the properties of the probability function, which is given by the Kolmogorov definition in the next class. Thank you.